Hey, Chem 30, welcome to topic number 4 of unit number 4, where we're going to discuss the acid equilibrium constant. So Ka and Kb are the acid and base ionization constants, respectively, and they're similar to Ksp. They talk about how much will convert from reactants to products, a ratio of that. It's made a little bit more difficult because the reactant in this case will be in the aqueous state, which means that we're going to have a denominator in our Ka and Kb equations where we didn't have that in the Ksp. So the higher the Ka value, the stronger the acid or base is. So we're going to look at these 6 acids here, 5 acids here, and the strongest of these acids will have the Ka with the exponent closest to 0. So in this case, formic acid is the strongest of these 5 acids, where hydrocyanic is the weakest. So hydrocyanic is HCN. Formic acid is actually this guy here. And we can see that this is a carboxylic acid, a very small carboxylic acid, which makes it actually quite strong. The Ka expression is just the product over the reactants for acetic acid. The products would be those 2 ions, the H plus and the acetate ion, and over the molecular form of acetic acid, which is CH3COOH. And then we've got a value here. And we'll be able to find these values in your reference book. So on the page that looks like this, at the top it says dissociation constants for acids. We can call these ionization constants. For polyprotic acids, there is an ionization constant for each ionization. So phosphoric acid, you'll notice there are 3. Sulfuric acid just says very large on here because the first one is such a strong acid, it doesn't have an ionization constant. We should recognize that the concentration of the hydrogen is equal to the concentration of the initial concentration of that acid. You'll also notice that hydrochloric acid or nitric acid or hydroiodic acid aren't on there because only weak acids will have an ionization constant listed on that table. Otherwise, they're just the Ka value is infinitely large, because if we imagine HI or breaking down, for example, we know that all of it is converted into ions. This at the end is 0 molarity. Let's say that this is 1 molarity, this is 1 molarity. Ka is equal to 1 squared over 0, right? So it's undefined. So we don't actually have Kas for strong acids or bases. So we're going to write the ionization expression for these 3 substances and then the Ka for it as well. So acetic acid we should recognize as being CH3COOH. If we're not sure of that, we can look on our little book here and it'll give us the formula. It's a weak acid, so we're going to use that double arrow. So this becomes CH3CO minus aqueous and H plus. Ka, right, because this is an acid, is equal to CH3CO minus multiplied by H plus over CH3COOH. Aniline, I'm not sure the formula of that one, so I'm going to look in my book. It ends in INE, which should trigger me to think that this is, oh, maybe this is an amine, and therefore it'd be a base. So it is, aniline is C6H5NH2. So we get C6H5NH2 aqueous combined with water, as we do with all weak bases, making C6H5NH3 plus aqueous and OH minus aqueous. And then we have to make sure that we're writing a Kb, right? This is a base. So we're going to get that C6H5NH2 plus aqueous multiplied by OH minus aqueous over C6H5NH, that should have been 3, pardon, NH2. There we go. And last but not least, propanoic acid. I spelt this wrong. This is actually spelt like PRO. There we go. It's in our book as well. So we can just flip the page back to our table of weak acids. And it's near the bottom there. So we get C2H5COOH or C2H5COOH. Really, this could be written as CH3CH2COOH. And now we can see where we're getting that propanoic from. This decomposes into CH3 CH2COO minus and H plus. All these are aqueous. So the Ka expression for this one is going to be Ka is equal to concentration of CH3CH2COO multiplied by K or H plus all over CH3CH2COOH. Notice that each time I wrote the symbol Ka or Kb, the whole expression, not just the numerator and the denominator, showing that I know that these are acids and bases. When a student would write something like this is generally out of a mark. I would give it 0.5 and a 1. Why? Because I want this Ka is equal to, I want you to show me the entire process there. All right, this is where we're going to get into those calculations involving Ka and Kb. While the acid ionization constant is useful, it's really the amount of H plus and OH minus that we care about. So we're going to take that Ka and Kb and do calculations to figure out the concentration of those ions, acids producing H plus and bases producing OH minus. And eventually we're going to take those numbers and do pH and pOH calculations. That's topic 5, in order to easily communicate how strong acids or bases are. So first now, our question here, or example, we've got a really easy one. We're going to calculate the concentration of H plus in a solution of hydrochloric acid in which 3.5 grams of gas is bubbled through 2 liters of water. So we make strong acids by taking the gaseous form of hydrogen and chlorine. When they are heated up, they will create hydrogen chloride gas, and then it's bubbled through water. And some of that HCl will actually dissolve into the water. So it'll go HCl gas into HCl aqueous. Okay. In this question here, we've got a mass of a gas, which doesn't really make sense, but it allows us to do an extra calculation here. So we should recognize that in strong acids, concentration of HA is equal to concentration of H plus. So if we can figure out the concentration of HCl, we can figure out the concentration of H plus. Hopefully you recall that concentration is equal to moles divided by liters. In this particular question, we're not given moles, but we can convert 3.65 into moles by taking our given mass, multiplying it by 1 mole of HCl is 35.45 plus 1.01. Sorry, 36.46, really stumbled on that one, which is equal to 3.65 divided by bracket 36.46 bracket equals 0.100 mole. Oops. Mole. So then we're going to take 0.100 mole divided by our 2 liters, which gives us 0.0500 big M. We know that when we have HCl, which is a strong acid, that's from that strong acid list that we need to memorize, breaks down into these 2 ions. So if this is 0.0500 molarity, this would be 0.0500 molarity. Okay, and we don't care about the chlorine. The question asks us the concentration of H plus. Easy one to start things off, okay? This one is a little bit more complicated. Why? Because we should recognize that weak acids only partially ionize. So how much they ionize is dependent on that equilibrium value. But it's not so easy because we got that forward and reverse process happening. So we've got this initial concentration where we might have only acetic acid, but an equilibrium is eventually established. So let's write out this reaction first. We've got CH3COOH aqueous. We can use the Bronsted-Lowry or the Arrhenius for weak acids. It makes sense to use the Arrhenius because it's just simpler. We get CH3COO minus aqueous and H plus aqueous. Now, let's imagine that we've got a solution in which we mix this acetic acid into. Then it tells us that we mix 0.25 moles of acetic acid into a liter of water. So we've got that initial condition, and eventually some of that acetic acid is pulled apart by the water. So there's a change, and eventually equilibrium is established. And if you're listening really carefully, you notice I've said 3 key words. There was initial condition, it changed by some factor, and then established an equilibrium. What's the best way to tabulate this information? You betcha, by an ice table. Okay, so we've got an initial concentration of our acetic acid as being 0.25 molarity. Now, most of the time I'm going to give you this number in moles per liter, but you might have to convert it as well. Initially, there was no acetic acid ions, there was no H plus ions. We took our, let's say, our chunk of acetic acid and put it into a liter of water. The moment that acetic acid hits the water, there's no ions yet. It hasn't been ripped apart. So we got 0 and 0. We know that this is going to go down by X, and this is going to go up by X, and this is going to go up by X. So we got 0.25 minus X, and we got X here and X here. So when we write our Ka, we get the concentration of CH3COO minus H plus over CH3COOH. And we can see that this is going to create a little bit of a problem for us. We know that 1.8 times 10 to the negative 5 is our Ka, is equal to X times X, so X squared, over 0.25 minus X. Yes, we've got a nasty quad in there. We can get around this. Recognize that this means about 1 in 10,000 particles of this solution will break down. 1 in 10,000. So that would be equivalent of 0.00001. Okay, so that's actually, it's technically 1/8, so a little bit more, but still a very small number. Okay, so we know that that's an incredibly small number. So we can think of this change, this X, as being essentially like $2, let's say. This is going to be $2. And this up here, while 0.25 doesn't seem very big, 0.25 compared to this number, 0.25, is massive. So we can think of this as being a billionaire. So if 0.25 is a billionaire, and let's say that this billionaire is weird, and he's got his $1 billion in loonies. So that would take up probably about the school. You'd need the entire school filled with loonies to get to $1 billion. Now, if someone stole 2 loonies from that horde of loonies, could you find it? Could you notice? No. It's going to be so small that it's insignificant. That's the same idea as taking 0.25, subtract 0.00018. And we're just going to make this 10 just for easy math. That changes this number to 0.24999. Is that really that different from the other one? No. And we can't be that accurate. It's like driving outside the city. And for fun, you go on the weigh scale with your vehicle. Okay, and you find out your vehicle is 1,800 pounds or 1,800 kilograms. And then someone hands you a bowling ball or a water bottle. So you've got this water bottle now. Is the number on the scale going to change? No, because it's not sensitive enough to notice that change in mass. Yes, the mass has changed. There's more water inside the vehicle, which then is going to make it heavier, but there's no way of telling that. Okay, so we can say that it's insignificant. So we're saying that it's insignificant here, and I'm going to highlight, we can say that X really doesn't actually matter here. In this situation here, X is so small that it doesn't contribute. Well, how come we can't just say that this is 0 and this is 0 as well? Well, we can think of these values up here, these X's or these zeros to begin with, as being something like a student. So this is a student. Why? Because they have no money. They're broke. Okay, this is a university student or a high school student. They have no money. So if someone gives a student $2, yeah, they're going to be able to find that quite easy. So from going from 0 to some number other than 0, that's going to be significant. Okay, these students have no money. They're able to go out and buy a little Happy Meal now, or a burger, a cheap burger from McDonald's. Okay, so the way we write this, we show this mathematically as 0.25 minus X is approximately 0.25. So what does that do? Well, it changes our denominator now. So this is 0.25. So when we solve this, we get 0.25 multiplied by 1.8 times 10 to the negative 5. So 1.8 times 10 to the negative 5 bracket times 0.25 equals, so this gives me 4.5 times 10 to the negative 6 is equal to X squared. square root both sides. I get x is equal to 2.12 times 10 to the negative 3. Now, if you left it here, 3 to 4, why? Because I'm looking, the question asks, what is the concentration of the hydrogen ion? The concentration of the hydrogen ion is symbolized by x. Right here, we solve for x, which is equal to 2.12 times 10 to the negative 3 and a unit, otherwise a half-point subtraction. Okay, so you can see that we're getting back into that calculation phase. This is a very easy calculation for the unit, so expect it to get more challenging based on the information that you might be given in the future. All right, calculate the hydroxide concentration in a 0.025 molar solution of aniline, a weak base with a Kb of 4.3 times 10 to the negative 10. All right, we're going to do the same thing here. So we're going to start by writing our equation. So C6H5 NH2 aqueous decomposes or plus water, right? Because we're having to use that Bronsted-Lowry definition. C6H5 NH3 plus aqueous and OH minus, initial change equilibrium. We know the initial concentration here is 0.025. We know that water is liquid, so it doesn't appear in this. We have 0 aniline ions and 0 hydroxide ions. This is going to decrease by x, 0.025, subtract x, increase by x, increases by x. So we get x, and dashes all the way down. Again, I always want to see this, or else I'm going to take a point deduction. I want you to show me mathematically how we're getting around using that quadratic expression. So this works out to being 0.025. There are some circumstances, and I'll show you one of these examples later on, when we can't make this approximation. Essentially, we're imagining this as being a billionaire, and I'll write this in red. We're imagining this to be a billionaire here, and this to be $2. A billionaire wouldn't spot $2 going missing. But let's say that this concentration was really low. So let's just imagine for a second this number, instead of being 0.025, 0.0015, and this, instead of being $2, was $1,000. Okay, yeah, now there's going to be a much closer relationship. Someone who has $2,000, if $1,000 goes missing, they're going to be able to spot that. For us, for the majority of this unit, we will not have to deal with that, okay? In fact, you'll never have to deal with it. I'm just going to show it to you as a matter of interest. So let's go back to solving this out. So we get Kb is equal to concentration of C6H5NH3 plus OH minus over C6H5NH2. So we get 4.3 times 10 to the negative 10 is equal to x squared over 0.025. Now, I'm not going to write out all the steps here. I'm just going to solve this in one go on my calculator. So I'm going to put in the scientific notation first, because that's always where mistakes get made. So I'm going to put that in, hit equals, so it's determined my calculator, multiply by 0.25. When you multiply by a number less than 1, it gets smaller. So expect that exponent to become more negative, and it does. 1.075 times 10 to the negative 11. I'm not going to bother writing that down. I'm going to hit my square root button, and because I have that answer key on my calculator, hit that, and I get 3.28. So 3.28 times 10 to the negative 6. And I can see that's the answer down there. But we want to make sure that we write this out. Concentration of OH minus is equal to 3.28 times 10 to the negative 6. And include our unit of molarity. Okay, so there's the second example of a weak base Kb calculation. Okay, welcome back. So we've got a couple more slides to go through here that is dependent on this idea of self or auto-ionization of water. So remember that water, just a cup of water or a glass of water sitting by itself, undergoes this process where it splits up into H plus ions and OH minus ions, right? So H2O liquid breaks down equilibrium here into H plus and OH minus. Okay. We don't see this H2O liquid because remember, liquids are not included in equilibrium expressions. So Kw, it turns out that the rate that this happens is 1.0 times 10 to the negative 14, which means about 1 in every 1,100 billions breaks down. So a very, very, very small amount. But as the concentration of one increases, the other has to decrease. So by putting acid in, we increase the constant or the concentration of H+, which means that this has to go down. When we've got a neutral solution, both of them are 1.0 times 10 to the negative 7. But as we increase hydrogen, OH minus decreases. Or if we're adding a base to water, which increases the amount of hydroxide ions, it drops at H+. It's easier to imagine this. Let's say that Kw, as an easy number, is 10. That we could have, or let's say 100. In a neutral solution, we have 10 times 10 equals 100. But if we increase the concentration of hydrogen to 50, that means we have to decrease the concentration of OH minus to 2 because we want it to get to 100 still, right? That constant is always there. This also means that if we know one, we can figure out the other because, so Kw is equal to the concentration of H plus and OH minus. If this is a constant, it means that it's always that. We can say that the concentration of H plus would be equal to Kw divided by OH minus, right? It's a little bit of order algebra here. We divide both sides by H plus to get it by itself, or we take and move the Kw on the other side. If we're trying to figure out the OH minus, this would be the formula. So Kw over H plus. Okay. So if we know that both of these things are, a neutral solution would be 1.0 times 10 to the negative 7. If we have more than that, then it must be either acidic or basic, right? So if we've got a concentration of H plus being 1.0 times 10 to the negative 3, which is 1,000 times greater, we know it's an acidic solution. If we've got 1.0 times 10 to the negative 11 of H plus, we know that it must be basic because the OH minus must be higher because the H plus is so low. Let's take a look at this example here. In an aqueous solution, concentration of H plus is 1.0 times 10 to the negative 13. What is the OH minus in the solution? Is the solution acidic or basic? So we're going to go, okay, Kw is equal to OH minus multiplied by H plus. We're trying to figure out OH minus, so we divide by H plus. This crosses off, divide by H plus on both sides, right? So concentration of OH minus is equal to Kw divided by a concentration of H plus. Kw is always 1.0 times 10 to the negative 14 divided by 1.0 times 10 to the negative 13. Remember, when we are dividing exponents, it's really subtracting. So we get negative 14 subtract negative 13. These really change to positives. So this becomes negative 1. So we get 1.0 times 10 to the negative 1, which is the same as 0.1 molarity. Okay, so the concentration of OH minus is equal to 0.1 molarity. This is much, much, much higher than 1.0 times 10 to the negative 7. So we have a very basic solution. Okay. Alrighty, that is it for topic number 4. As always, any questions or concerns, email me. Otherwise, have a great night, Chem 30.